For the second part of Notes 20, let's start talking about how we can decide how good our simple linear regression model is. One thing that we're going to use is something known as the R-squared value, or occasionally called the coefficient of determination. And we saw that the sample correlation is denoted by the letter R, and it can tell us the strength and direction of a linear relationship. And the R-squared value is actually exactly what it sounds like. We're just going to take that correlation and we're going to square it. And the reason why we're going to do that is because it gives us a nice interpretation about how well our explanatory variable is helping us explain the response variable. And exactly what it's doing is the R-squared is measuring the proportion of the variability in our response variable that can be explained by the explanatory variable in our data. And just a quick note is that if you didn't have a y-intercept in your model, the coefficient of determination, or the R-squared, wouldn't actually have this meaning. So we won't see any cases like that in our class, but it's something to keep in mind. So let's look at an example. In a previous Stats 212 course, students measured the length of their hands and their height, and we found that the correlation between length of hand and height was 0.82885. So we are going to use that to calculate the correlation, or the coefficient of determination, the R-squared, and then we're going to interpret the number that we get. So first, in terms of calculating it, let's just take that 0.82885, we'll square it, and we get 0.687. And usually what I like to do is convert that to a percentage because it's going to make my interpretation a lot easier. All right, so this is telling me the proportion of the variability in my response, height, because that's my y variable, that can be explained by the explanatory variable. So in this example, 68.7% of the variability in student heights in our data can be explained by the student hand lengths. So essentially, knowing a student's hand length, you can explain a lot of the differences that you see in height from student to student. Now, I'm not going to know exactly how tall a student is just based on their hand length, but I'm going to have a lot better idea than if I didn't know that information. So another way to think of it is if you just made a graph of everybody's height, there's a lot of variability there. Some people are on the shorter end, some people are on the taller end. Now, if you used hand lengths to make predictions for the height, how much you're off by in your guess will be a lot smaller than if you just looked at the original graph and had no other information. So if you want to, pause the video right now, this might be worth doing, and answer this next question. So it's going to be the exact same thing, but now we're going to look at height and shoe length, calculate the R-squared, and write a sentence for the interpretation. All right, and hopefully you paused the video and took a chance to do that, but I'll walk you through what it would look like if we did it. I'm going to take that correlation value again and square it. I get 0.554, or 55.4%, and that means that 55.4% of the variability in student heights in our data can be explained by the student, and this says hand lengths, it should say shoe lengths because we're looking at this new variable here. So what is this telling us about trying to predict student heights? Well, it looks like the model that uses hand length is a better model. So remember that our goal here is to talk about how good is our model. And what we're seeing is that hand length explains a greater percentage of the variability in student heights than shoe length does. And we actually have a good explanation for why that would be. Hand length is actually a physical characteristic of a person. Shoe length is sort of like foot length, but then there's a little bit of extra sort of noise and variability because people's shoes are different. Some might have kind of more area, some might have less. And so I imagine that if we compared hand length to hand length to foot length, those would be a lot more similar. But in this case, it looks like hand length does a better job. So there's another example here. Again, I would recommend pause the video, read the example, and try it on your own. I will go through it at the same time right now, though. We've got a scatter plot on the right-hand side. I'm telling you that the r-squared value is 0.9335, and I want you to go the opposite direction. I want you to tell me what the correlation is based on the r-squared value. And I've got a little note here that says, be a little bit careful with this. So we might realize that since we can square the correlation to get the r-squared, then we should be able to take the square root of the r-squared to get the correlation. And for the most part, we can. But we need to remember that actually, if this was positive or this was negative, both of those would give us 0.554. So when I take the square root, I'm going to remind myself that actually my correlation could be positive 0.9662, or it could be negative 0.9662. And so which one that is, I should look over at my graph here. Notice that I've got a negative slope. It's going down, which means that this must be the negative version of that. So my correlation is negative 0.9662. So this was just a chance for you to think about how correlation and r-squared are related. All right? So let's continue on to the next page and talk about one other important thing that we can do with our simple linear regressions. We've talked about making a confidence interval for the slope, and we've talked about making predictions using our line. But one of the things that we're probably most likely to actually be interested in is some sort of confidence interval for our prediction, because we know that our prediction is not going to be exactly right. And so just like everything else this semester, we want to be able to give people a little bit of wiggle room. We don't think our answer is going to be exact. And so we've seen throughout the semester that a confidence interval will give me a range of likely values for a parameter, so a population mean, for example. But we're going to learn about something new here, something called a prediction interval, which is very similar, but instead of giving a range of likely values for a parameter, a prediction interval gives us a range of likely values for an individual at some specified value of the explanatory variable. So let's think about what that means. I've got a few questions below, and I want you to think about whether each of these would be answered with a prediction interval or a confidence interval, and what kind of context you're using to decide that. So take a few seconds, pause the video, try it out. And when you come back from pausing that, I will go through these. So the first one says, what is the mean calorie content for burgers with 35 grams of fat? And I've got highlighted here that we would use a confidence interval because we're talking about the population mean for all burgers with 35 grams of fat. And so that word mean here is what's sort of our context that we're using. On the other hand, if I said, what will be the calorie content for a specific burger that is going to have 35 grams of fat, that's going to be a prediction interval because I'm talking about one burger. It's just a single prediction, and I want to know how much that prediction may or may not be off by. So words like specific tell me that I want a prediction interval. Similar situation, suppose I'm testing or predicting test grade based on number of absences. I want to know the mean test grade for students that have been absent 3 times. That word mean is in there, which tells me that I'm interested in a confidence interval. On the other hand, if a student says, oh no, I've missed 10 days of class, what grade do I expect to get? That's going to be a prediction interval because they only want to know about their grade, not the average for all students that have missed 10 days of class. All right, so you'll look for some of these context clues if you're asked whether you should make a prediction interval or a confidence interval. And we're going to talk about both of these, but we'll start with confidence intervals. Again, just to remind you, there's a general form that all confidence intervals have, and this is the actual formula. So if we want a confidence interval for the population mean response, when the explanatory variable is, this says x0, but it would just be some number. So up here, like 35. So I would plug 35 in where it says x0. That equation's a little bit of a mess, so instead we will use SAS, and all we need to do to get confidence intervals is just add onto our code that we're already using. On the line that starts with model, we're just going to add slash and the letters CLM. And CLM stands for confidence limits for the mean. All right. So we can do this with the burgers data set, and I'll go and try that out real quick. Let me bring up the burgers data set, and it's taking a few seconds here to load. I'm going to copy this into a different window so that it lets me make edits, and I'm going to type out my code here. Data equals burgers, model, and we are trying to predict the calories using fat, and I'm adding slash CLM so that I get these confidence intervals, and run. And if I run all of this, we'll see the output that we get here. And you can see that if I scroll down, I do have something that says 95% confidence limits for the mean. The problem is I don't know which of these confidence intervals I want. And what it says in the notes is that we are going to get a separate interval for every x value in our data set. So I can look at my data and see that, I'll go right here, on the fourth line, that burger had 35 grams of fat. So the fourth confidence interval in my output will be a confidence interval for the population mean number of calories for all burgers with 35 grams of fat. So I'll go here to my results, I'll go to my fourth observation, and my confidence interval goes from 548.4 to 620.1. And that should be what I have here in the notes. And if you wanted to interpret it, we would use interpretations just like we've used for other confidence intervals. I am 95% confident that the population mean, in this case we're talking about number of calories, is between 548.4 and 620.1, and then specifically, this is for fast food burgers with 35 grams of fat. We'll see on the next page that the code and the output and everything for prediction intervals looks very similar, but that'll be what we'll pick back up in our next part of this video.